In part one, we talked about the helium-4 energy levels, and we came up with an estimate for the sensitivity of an optically pumped magnetometer, which is what we're talking about here. And we came up with this expression as an approximation. Now in part two, we want to talk about the optically pumped magnetometer system. And just as in part one, this entire three-part, possibly four-part, is being done in memory of a friend of mine, Don King. And he and I worked on optically pumped magnetometers and things beyond that over most of my working life. Now in part one, we talked about the different energy levels associated with the optically pumped magnetometer. We talked about the pumping light, how the energy levels change. We showed how when we apply the right frequency, we can mix up the distribution of electrons in certain levels in the helium-4. And the main part of that, besides coming up with the expression for the sensitivity, was to come up with a resonance signal. And we talked about that a little bit, and we're going to talk about that a little bit more. So what we want to do now is move on to an actual helium-4 magnetometer. So it's sketched out here. We begin with a helium lamp. The lamp is lit by a high-frequency oscillator, and it puts out all different colors, mostly blue. And that high-frequency oscillator is also connected to the helium sensing cell, the helium-4 sensing cell. And we want to get just the light that we're going to use for the optical pumping through. So there is a lens, a filter, and a polarizer to do that. So there's also a filter too, a light filter, to have mostly the 1082 nanometers going through the cell to pump the atoms. And then the light goes through the cell and falls on a detector. Another component that and the discharge also is applied to the helium cell to get the helium atoms into the metastable level, where the Zeeman effect takes place. So the light goes through the cell onto a detector. And the other component here that I want to mention is that we have coils around the cell, and that is where we put in that resonance frequency, which gives us the resonance curve that we talked about earlier. So what happens is the resonance frequency that's applied to the cell, and remember that's what mixes up the electrons in those three levels, that is being swept. So the frequency that's actually applied is the resonance frequency plus or minus a little bit frequency one way or the other. So it's a nu plus or minus a delta nu. And it's being swept at about a 500 hertz rate. So the light falls on the detector and it goes to a phase sensitive detector. The phase sensitive detector is seeing what the IR sensor is seeing, the light, and it's also seeing the sweep frequency that's being applied. And what that means, if we go back over here, this represents that sweep frequency. So the resonance oscillator is being swept back and forth a certain amount. When we're on this side of resonance, we see a signal come out that looks like this. If we go on the other side of resonance and we sweep back and forth, we see a signal that looks like this. And although we're sweeping the same way, when we look at the signals that come out, they're out of phase with respect to one another. So if we get a phase like this, we know we're too low. If we get a phase like this, we're too high. Phase between this and this and this and this. And when we're right in the Goldilocks region, we're locked on we're on resonance, and we have a signal that looks like this. So the phase detector looks for this. If it's too low, it will apply a voltage to the voltage-controlled oscillator, and that will increase the resonance frequency that's coming out and going to the cells to scramble up the electrons in those levels. If it's too high, the voltage will decrease, the resonance oscillator frequency will decrease, but eventually you get to the part where you're at that Goldilocks region, you're right on resonance, and then the error signal of the DC voltage that comes out of the phase detector from the comparison of what's here and here would be 0, and then we're able to track the magnetic field as it changes. If the field goes up a little bit, the voltage will appear here slightly, drive the resonance oscillator a little higher, and then it'll eventually become 0 again. And so we have what is a locked loop, a locked resonance loop. And the frequency that we apply, again, it depends on what the magnetic field is. It's directly proportional through the gyromagnetic ratio. So as an example, if the magnetic field of the Earth is 50,000 nanoteslas, the resonance frequency will be 1.4 megahertz. And the resonance oscillator, this voltage-controlled oscillator, the low end is about 0.6 megahertz, and the high end is 2.2 megahertz, corresponding to low Earth field values of around 20-some thousand nanoteslas, all the way up to roughly 75,000 or more nanoteslas. So that's the process that goes on to get the magnetometer working. And again, this high frequency oscillator, that's what lights off gives us the light from the lamp and lights off the cell. It's a discharge process, and that process allows us to have atoms in the 2-triplet S1 state. The pumping light takes it up to a 2-triplet P0 state. Electrons will fall back down into those 3 levels that we showed in part 1 that are split by the magnetic field. And if we put in, say, sigma plus right-hand circularly polarized light, we'll remove electrons from this level. They'll go up to here. They'll fall back down with equal probability. But the continuous use of the pumping light will get those located in these 2 levels. And then by applying the E equals h nu, we scramble up those levels and get them redistributed, and that's how we get the resonance signal. So again, the frequency is proportional to the magnetic field. The specific example here is 1.4 megahertz is 50,000 nanoteslas. And the energy of that spacing, if you work it out, it works out to 5.8, the spacing here, of 5.8 nano electron volts, a very, very small amount. And so the result of the 1082 nanometers, that the pumping light, that's more or less the purple line here, which will also get us to this level 2. And then the scrambling with the E equals h nu will get us to either this level or this level. So it gets all scrambled up, all redistributed again. So that's the redistribution that's taking place. So now we're locked onto the magnetic field. As the magnetic field changes, the resonance oscillator frequency will change because of the sweep that's on it, and we stay locked onto that Goldilocks region. So now we have a frequency. What do we do with that? Well, we want to change that frequency to a voltage, and we do that through a frequency converter. So that resonance frequency nu goes to a voltage. That voltage then comes out and goes to a display, to a chart recorder, and the old one used to be called the RO32. So if you're over the ocean and you want to try to find a submarine, you're flying with a magnetometer on the helicopter, you might see a signal that looks something like that. So that's the idea of the entire system, is for anti-submarine warfare. And now over here is an actual picture of a system. This is called the ASQ-81 magnetometer. And this is the service, this picture here is actually the service test engineering model. That's STEM, service test engineering model. And now if you imagine what we have up here, and let's rotate it 90 degrees so the lamp is on the top, that's what you're actually looking at here. This is the helium cell behind this black plastic housing. You can see a little bit of the cell here, and the discharge is on. You can see the cell glowing a sort of purple color. When you see this, it reminds you of the blue bonnet in Texas. It looks very similar in color. And then up above here is the lamp. For you to be able to see the lamp a little better, I exploded it up here in this view. And you can see this cylinder running across here, this glass cylinder. That's the lamp, and there are metal clips holding it, and that's what's making the contact with the high frequency oscillator to get the lamp glowing. There's a similar arrangement on the cells. So the lamp is above here, and in this area here are the optics, the filter, the lens, and the polarizer. And on one side we have left hand circularly polarized light, on the other we have right hand. And the reason for the left and right hand is a story all in itself, but we're not going to go into those details now. And the IR-detector here, that is shown, that you can't see it too well, but it's right down here at the bottom of the cell. This is a view of the other side of the magnetometer. And the magnetometer actually has three axes. They're called A, B, and C. And I'll explain in a moment why we have the three axes. Now if you look at this cell here, this is the C axis, and I think this is the A axis. You can see these coils wrapped here. They're the Helmholtz coil that I told you about that applies the frequency to the helium cell. And the IR detectors are here. Light comes from this lamp here, actually lights both the A axis and the B axis. There's one lamp for that, whereas so that one lamp lights two axes. The lamp for the C axis just lights one, or works for one. And you can see the lenses over on this side. And of course those lenses and filters and polarizers are in here. One other thing to note about this is if you look closely, you can see these wires. They're twisted pairs. And one of the reason they're twisted pairs is because you don't want to have extraneous magnetic fields generated by any current flowing in there influencing the magnetic field that you're trying to measure. So when we talk about having three axes, a lot of people say, well, you're taking the square root of the sum of the squares of the three axes, but no, you're not doing that. And let me explain why we have the three axes. Let's say this is our resonance signal. And we'll say the size of the resonance signal is a signal S. Now, if this is the pumping light direction, which in this case is down here and this way on that cell and the other way to that other helium cell. So this is the pumping light direction. And let's say this is the magnetic field direction, and we'll call this angle theta. This is not the scale. And it turns out that, speaking very approximately, that signal is proportional to the cosine squared of theta. So now let's say we have the three axes. A, B, and C. And out here is the magnetic field. Let's say it makes an angle small a with the A axis, small b with the B axis, and small c with the C axis. And now that signal is going as the cosine squared of theta. So you can think of, on the a-axis, the signal would be s cosine squared a. On the b-axis, and we're going to add them. On the b-axis, it would be s cosine squared at angle b. And then on the c-axis, it would be s cosine squared the angle c. And from the law of the direction of cosines, cosine squared a plus cosine squared b plus cosine squared c is equal to s. So that way we keep a constant signal. So what happens is all the light that falls on those different IR detectors, it's basically summed. And that's how we get a constant signal. And so in actual use for anti-submarine warfare, we're showing a sketch here of a helicopter flying over the ocean with a submarine down below. And after we converted that resonance frequency to a voltage and put it on the display, we might actually get a signal if we pass over that submarine. And that's the main use of this system, but we've also used it for measuring magnetic fields generated by ocean waves, micropulsations in the geomagnetic field, and very interesting geologic structures. So this picture shows a reeling machine attached to a Navy helicopter, and here's a towed bird, and inside that towed bird is the magnetometer. And I don't know if I mentioned or not, but this is almost to scale with my hand. So that gives you an idea of how big that sensor is. So that's the diagram that basically outlines how the system works. It turns out that this is a 50-year-old system. And there have been many improvements made from what I described here. And I guess I'd like to point out that 50 years ago, roughly, when these systems were being made, this was practically the only text that you could find on optically pumped systems. Title is Optical Pumping: An Introduction by Bernheim. And now there is a very good book out by William Happer at Princeton and others. It's called Optically Pumped Atoms, and if you want to learn more about the details of the actually optical pumping process, this is a very good book to look at. And finally, if you want to look at the actual use of the optical pumping in a magnetometer, this book by Butker and Kimball is good. It's an edited book, so there's sections done by different people, and one of the really good sections is done by Slocum of Paul Atomic. And so that about covers it, and there are some very interesting things that are being done with optical pumping. And one of the things I would recommend is for those who are interested, you could do a Google search on Princeton and Lorentz Violation. And the name of the person is, I think it's R-O-M-A-L-I-S. So if you do a search on that, you'll find something that comes up that's very interesting. And when you hear the term, people go to the ends of the earth to do things, well, they actually went down to the South Pole to do an experiment. involving things associated with the optical pumping process. And one of the things they have something called a I think it's a gyroscopic effect. And if you say this is like 25,000 nanoteslas, this is minus 25,000 nanoteslas. In the Princeton area, and this represents something associated with the orientation of the sensor that they're working on, it'll look something like this. I'm just recalling this from memory. This is not exactly right. And that's what you see in Princeton. And this represents something they would like to get rid of. And if you go down to the South Pole, because of the rotation of the Earth, they're trying to get rid of certain aspects of the rotation of the Earth. You're down here. So it's a very interesting application that involves optical pumping being done down at the South Pole. And last time I looked at this was a couple years old. So I would recommend you take a look. Put those words in, do a search, and it'll pop up.